All right, young scientists, it's time for our third and final screencast here in AP Chem Unit 7 Thermodynamics. We're going to talk about electrochemistry, the chemistry of electricity. Electrochemistry is really all talking about reduction, oxidation, or redox reactions, which you've already learned about. Remember our mnemonic, Leo the lion goes grr, losing electrons is oxidation, and gaining electrons is reduction. If you need a recap on redox reactions, there's a link to a video here that you should find helpful. Now, our primary focus here is going to be about voltaic or galvanic cells. These are made of several components that we're going to list out here, but they'll be a little easier for you to see in a diagram in a couple slides. We're going to have the anode, where oxidation is happening, so where we're releasing electrons. The cathode, where reduction is happening, so where we're absorbing electrons. The electrons flowing from the anode to the cathode. We'll also have a salt bridge, so that we don't have a bunch of positive charge or a bunch of negative charge building up on either side of our voltaic cell. And through that salt bridge, we'll have some anions flow to balance the charge. Now, with this, we're going to have what's called cell potential. This is the force or the voltage that's pushing the electrons through the wire. Now, when you do this, it's really just an E. Sometimes you get this Greek letter instead, but it means the same thing. E of the cell is the electromotive force, the force that sends electrons through a circuit. We measure it in volts. If we actually want to measure it in an experiment, we usually use a voltmeter or sometimes a multimeter, which can measure voltage or amperage or resistivity. Now, for most metals, there's already known and well-measured reduction potentials that you can look up in a table. I'll be providing that table on Google Classroom. Just know that all of those are measured at standard conditions, so 25 degrees Celsius, and 1 molar concentration solutions. Now here we have a pretty in-depth model of a voltaic cell where we have pieces of metal on each side. In this case, we've just written M for metal. We also have solutions that they're submerged in. They're connected with a wire as well as a salt bridge. Now what's going to happen is the electrodes are going to flow out of my metal through the wire and to the other side. Whereas those electrons are now present here, they'll attract positive ions from the solution and they'll actually precipitate out as a solid onto this side. Meanwhile, as the electrons leave, we're going to also release positive ions over on this side. Now, this is a pretty in-depth picture, so you can stare at it a bunch if you want, but I think we're actually going to move along and look at a little bit simpler ones here in just a second that should be easier to follow. Now, we've already learned about half reactions when we did redox reactions. And that's going to, when we put the half reactions together, that'll tell us the total cell potential. Now, but since we already have all of these listed as reductions, instead of adding the half reactions like you would do to put a redox reaction together, we're actually going to subtract, because what you're really doing was adding a negative. So our total E of the cell is going to be our E of the cathode minus the E of the anode. And sometimes you might struggle to decide which one is the cathode and which one is the anode. What you're going to look at is which one of the two cell potentials in the table is greater. That one will be your cathode. Actually, usually we'll have a positive cathode and a negative anode, so that when we subtract a negative, we're actually adding two numbers together and getting even more voltage as a result. That's ideal. It won't happen every time, but it will happen often. So here we have our diagram of a voltaic cell. This is also could just simply be called a battery. So we have a copper anode, a piece of solid copper, and a silver cathode, a piece of solid silver. They're both submerged in solutions. Here we have, so this is copper with some nitrate, that's some NO3, and silver with some nitrate, some NO3. And they're connected by a wire. Now this is going to allow the electrons to flow from the copper to the silver, and we can see if we hook up a voltmeter that we would get a voltage here. As the electrons leave the copper, we're going to release copper plus 2 ions into solution. And as the electrons come to the silver, they're going to attract silver plus 1 ions, which are actually going to stick and become a solid on this silver. So what you'll see over time is this copper anode will slowly dissolve and disappear. It's not because the copper doesn't exist, it's just all in solution. And the silver cathode will grow as more and more silver collects upon it. Now what we've done is connected these two with a salt bridge, and the simple way to do this is just have a damp piece of paper or like a string, something that water and ions can flow through. And it's a salt bridge because it's got some sort of salt, in this case KNO3, potassium nitrate. As we release more copper ions on the left, this solution will become more and more positive, which will attract nitrate ions to this side in order to balance the charge. And the reverse will happen over here on the right. As silver leaves, this side will become more and more negative, which will attract potassium ions to balance it out. So the salt bridge allows, or really it prevents a buildup of charge, which allows electrons to keep flowing. Now what I want you to try to do is sketch your own cell using zinc and copper. So you need to make sure that you have an anode, a cathode, and the direction of flow of the electrons. You're going to calculate the cell potential, E of the cell, like we talked about 2 steps ago. Assume that your solutions are 1 molar zinc and 1 molar copper, so they'll be what it appears as on your reference table. And again, you can use KNO3 as your salt bridge, just like the last one, show where the ions are going to flow. Now I'm going to encourage you to pause the video here so you can make your own drawing. But when you're ready, go ahead and unpause and we'll go to the next slide. Okay, hopefully you've got a picture that looks something like this. You've got your zinc on one side and your copper on the other. Now this drawing doesn't have all of the things I asked for from you because I couldn't find a perfect one, I'm sorry. It does have the flow of electrons from the zinc to the copper, as well as the zinc going into the solution and the copper coming out. Now again, this picture isn't perfect. Instead of a salt bridge, what we have here is what we call a porous disk. This is a material that ions can move through. So our sulfate ions will actually move across the porous disk to balance the charge and accomplish the same task. Hopefully your drawing looks something like this. We also say E of the cell is 0.34 minus negative 0.76. So again, you see how we're subtracting, but it's a negative value. So really we're going to end up with more voltage and we get 1.10 volts. Now, because scientists tend to be lazy and they want to do things more quickly, or perhaps you could say more efficiently, we have our line notation that has the anode becomes the anode ions. We put a little double line to separate. And the cathode ions become the cathode. Or really, the anode plus the cathode ions become the anode ions plus the cathode. So go ahead and write that line notation for your cell here. And if you need to go back and reference which side is the cathode and which side is the anode, you can look over here. Don't get confused though, because the copper may have switched roles. Do you have it down? Our line notation will be zinc becomes zinc plus 2, and copper plus 2 becomes copper. So if we go here, it'll be zinc goes to Zn plus 2, and Cu plus 2 becomes Cu. Now we can also, as we've mentioned, concentration is important here, and we can change the cell potential by changing the concentration. Think about it with equilibrium, with Le Chatelier's principle. If we shift the reaction to the right, if we make more products, that'll increase the cell potential because you're trying to make more electrons move through the cell. But if we shift left, if we make more reactants, we'll decrease the cell potential because electrons can't move as easily then. So in this reaction, if Al plus 3 concentration is changed from 1 molar to 2 molar, what happens to the cell potential? Go ahead and pause the video to think about it and answer it. Okay, since we're increasing the concentration of a product, we're going to shift left to the reactants, which would decrease the cell potential in this scenario. We can also have the same setup, but have the same metal on both sides and have the thing forcing the electrons through be a difference in concentration. This is usually a pretty weak cell. I'm not going to spend a lot of time here because it's the same setup. It's just that if you look on this one, we have 0.01 molar versus 1 molar copper. So the ions will flow to generate equilibrium until the concentrations are the same. So we'll have electrons leave this copper and come over here to remove copper ions and drop the concentration on this side, and add copper ions and increase the concentration on this side until they're the same on both. Looking at this cell, if the concentration of silver ions was increased, what would happen to the cell potential? Again, pause. So, if the silver concentration was increased, if we're adding reactants, we generate more products, which will increase the cell potential. All right, so I was mistaken at the start of this video. I'm running into my 15-minute time limit here, so we're going to pick up with electrolysis, and that should be the final video of this unit. That'll be the next thing.